Alright, good morning. So this is going to be the lesson on Newton's first and second law. We have already done the lesson on Newton's third law, and that's the law of equal and opposite forces reaction. So an example of that was if you take a soccer ball and it's sitting on a grassy field, and you run by and you kick it with your foot, you apply a force to the ball, and then at that instant that ball applies that same force to your foot, and then right after that instant the ball would go flying and your foot would follow through. So the Newton's third law is just that whenever two bodies interact, they will always have equal but opposite forces applied to them. The ball will go flying more so because of the mass of it and its inertia rather than your foot. But your foot will still feel it. Alright, so now we're going to Newton's first and second law. So first, before we get started, there's something called inertia, which is pretty much the tendency for any object to want to stay in its motion or stay still. So an example is that ball, when it's not moving, wants to stay not moving. Or if you kick a ball and it starts rolling down a flat surface, it actually wants to stay rolling. It wants to stay moving in that direction. The only thing that kind of stops it is friction. If friction wasn't there, it would keep going. Kind of in space. If you kicked a soccer ball, it would go for a really long time because it wants to keep going. So Newton's first law is a body will continue forever at the same speed unless an unbalanced force acts on it. Okay? Unbalanced means there's no equal forces. Kind of like if a ball is sitting on a flat surface, it has a force of gravity working down on it. Okay? But it's not going down. So what's stopping it from going down? It's the force normal of the surface that it's sitting on. Okay, so these are called balanced forces. You have one down and one up, and they cancel out. Okay, that's why it's not moving up or down, because it has balanced force. But as soon as you put in an unbalanced force, that causes movements. It means that you don't have an arrow on the other side stopping it from moving. Okay, so if you kick something that way, you're going to do kind of an F push. That would be something called an unbalanced force, because there's not something exactly equal on the other side stopping it from rolling. Okay? There would be a force of friction, okay, but it might not be as much as the force push. Okay? Alright. And then I'll just quickly state Newton's second law, and we can go try some questions. So Newton's second law is an unbalanced force. Okay, so an example is like your kick. It's still, and then you kick it. That's an unbalanced force. It'll cause movement. It means it doesn't have an equal force yet on the other side. Will cause acceleration. And then it gives you this formula here. So I don't really remember this formula. The formula I use is just our classic force equals mass times acceleration. It's the same thing. They just solved for the a variable or the acceleration. Okay, if you solve for a, you divide by m, and that goes on the other side, and that's that equation. Okay, so this is, I guess the toughest one in my opinion is Newton's second law, because that's where you do most of the calculations. An unbalanced force will cause acceleration. Alright, so let's try some questions and just see what this all means. Okay, so it says if a pen is on your desk at rest, so this is my pen with a little cap on it. It's on rest, and this is the desk. Rest means it's not moving. Can you say that no forces are acting on it? Okay, so generally forces cause movement, right? This is saying if it's not moving, is there no forces acting on it? So the answer is no, because you still have gravity acting on it. It's just not moving because you have a equal and opposite force upwards of the desk acting on the pen, which is the normal force. Okay, so it's not moving, but there's still forces acting on it. The desk is putting a force on the pen, and gravity is putting a force on the pen down. Okay, so here it says, if the forces acting on the pen are balanced, is it correct to say that the pen is at rest? And the answer here is no. I guess the question would be, why not? If the forces acting on the pen are balanced, is it correct to say that the pen is at rest? So let's say, for example, if you drop a pen and it's falling, you have a force gravity on it. Okay, but let's say the air friction is equal to the force of gravity. Okay, but it would still end up falling. This is what happens when people are free falling off of a plane of some sort, and it just means that the pen would have no acceleration, but it would have a certain velocity. Okay, another example is if you kick a ball and it's rolling at 5 meters per second, and say you maintain the kick or the force on it, and you make it equal to the force of friction on it, it could still be rolling at 5 meters per second. It's just not accelerating in any direction. So you can have balanced forces on it. It just means that there's no acceleration. There still could be movement, but it just means there's no acceleration. Alright, so those were sample questions of Newton's first law, or of inertia. And a good example of inertia is when you're in your car and you make a turn. You're making an acceleration because you're turning, or you're changing the vector, and you're changing the direction. So let's say you're in your car and you turn left. What does your body do? Your body seems to turn right, right? But it's not turning right. It wants to continue going forward, but the car turns left. Okay, so it seems like you're going right, but your body actually wants to continue forever forward. But that's why your body kind of seems to go right when you turn a corner. Alright, so number 3, a 45 Newton block is being pushed along a floor where the coefficient of kinetic friction is 0.33. If a force of 25 newtons is applied, at what rate will the block accelerate? The mass of the block is 4.60 kilograms. So that's a lot of words. I'm just going to draw the picture. We have a block, and it says a 45 Newton block. What that means is the force of gravity is 45 newtons on this block. Alright, the coefficient of kinetic friction is 0.333. So I'll just write that down. And now we have this block. A force is being pushed of 25 newtons. So I'm going to put that in. Person's pushing to the right, I'll say. And then we know there's going to be some force of friction, but we don't know what that is quite yet, but I'll still draw that in. And we know there's a force normal of the ground acting upward. And we know that's going to be the same as force of gravity of the block. Okay? It's because the ground is flat. So now it's saying, at what rate will the block accelerate? So generally with these types of questions, which is Newton's second law, an unbalanced force will cause acceleration. We're going to be pushing more than the force of friction, which will cause it to move to the right. This means that the force will be unbalanced. How you usually start these questions is your F net, or your overall net force, is going to be one minus the other. And that's generally always how you do these questions. Your F push minus your force of friction. We know these two are balanced forces, but these two will not be balanced because it's going to be moving. Okay, so it's called an unbalanced force, and you have to know what the overall net force is when you go this minus this. Okay, so that's what I wrote. The net force is going to be this minus this. So now let's just fill in anything that we know. We know the force of the net, we don't know. Okay, so I'm going to leave it as that for now. Our force push is 25, so we can fill that in, 25 newtons. And then force of friction is, we know that's mu times Fn. We know the formula for force of friction is that, so let's fill that in. So now we're at this point. All right. So we have F net is equal to 25 minus mu, which is 0.33. And then force normal, which is the same as our force of gravity, which is 45 newtons. Okay, so now we have everything over here. We can solve for F net, where it already is solved for. So we can go 25 minus 0.333 times 45, and we get 10.015, and we know it's newtons because it's a force. 10.015 newtons is not the acceleration, but it's the overall the net force that's acting. You're pushing by 25, but it's actually only moving by 10 because force of friction takes away some of that. So here we know force is mass times acceleration. So we can go, our force is mass times acceleration, and then copy down our right side. Our mass we know is 4.6. And our acceleration we don't know. Now we can solve for our acceleration by dividing. And we get 2.177. What unit? It's acceleration, so it has to be meters per second squared. Alright, so if you constantly put a 25 Newton force on this block, force of friction is going to be taking away that much. So overall it's going to be accelerating by 2.177 meters per second squared. Alright, so now onto this question. Question 4. It says, what is the mass of a paratrooper who experiences an air resistance of 400 newtons and an acceleration of 4.5 meters per second squared during a parachute jump? So I would say this is one of the toughest questions for Newton's laws. We got a parachute, but we're going to do it the same way as we started that last question. So you have a parachute, and let's just put in all the values. Air resistance of 400 newtons. So that's a force, I'm going to say a friction, going upward of 400 newtons. Okay, it's the air that wanting to keep you up. And then you're also going to have a force of gravity pulling you down, which they don't really tell you your mass, so we don't really know what this is going to be. We can say it's 9.81 times whatever mass we are. So I'll do that. And it's saying an acceleration of 4.5 meters per second squared. Okay, so that's how fast you're actually going, falling down. So let's start out the question how we normally would. Our force net is going to be the direction you're going minus the direction opposing you. So this person is falling, so it's going to be, this one's going to have to be greater. Okay, because if you're going down, the force has to be pulling more so than the one that's keeping you up. So it's going to be force of gravity minus the force of friction. Okay, so our net force is our overall force, which is causing us to go down. So let's fill in anything that we know. Let's change F net to mass times acceleration. We know our Fg is 9.81 times our mass, and then our force of friction is just 400, so we can just fill that in. Okay, so now I have this. We know that our overall acceleration is 4.5, so we don't know m, but I'll put 4.5 for our net acceleration. Okay, so our net acceleration is 4.5 meters per second squared. That's how far you're falling after you've minused the force of friction. Okay, and then we have 9.81 times whatever mass this person is minus the 400. One thing to notice is I'm not putting negative 9.81 as the gravity. We do know it's down, but I'm keeping everything positive. How I incorporated the different directions is I put this negative here. I put that negative there. I knew that gravity and the force of friction are in opposite directions, so I minus the 2, and I'm going to keep all the variables positive because I know that they're already opposite directions. Okay, so here we have these two. We got to solve for our m, and then we have the question done. So I'm going to add the 400 over there and minus the m times 4.5. So it'll be 400 equals 9.81 m minus 4.5 m. And so 9.81 minus 4.5 is 5.31 m. And the 400 is still over there. Now we got to solve for m, so let's divide by 5.31. So we get 75.33 kilograms. So that's how much that person weighs. So again, that's one of the, I'm going to say probably the toughest type of question you can get for Newton's second law. It's your net force after you've subtracted two forces that work in opposite directions. Alright, this last one. A force of 50 newtons accelerates a 5 kilogram block at 6 meters per second squared along a horizontal surface. So horizontal surface, we got a block. It is 5 kilograms. And we know that someone's pushing at the push. And we know force of friction is opposing that force. So it's saying a force of 50 newtons. And then force of friction, it doesn't say anything about. Alright, so let's start it out how we normally do. We have two opposing forces. Let's just say our net force is going to be, well, if you're pushing it, the push has to be more than the force of friction if there's going to be movement. So I'll go F push minus force of friction. Alright, so our F net, our push is 50 newtons. Our force of friction, we don't know. And I guess here, our force net is just mass times acceleration. So let's fill in what we know. We know 5 kilograms, so we can take that for the mass. Our acceleration net, after you've subtracted the force of friction, is going to be 6 meters per second squared. So I put that in for the acceleration. We have 50 still, and we have force of friction there. Okay, so now I can solve for force of friction. We can add it to the one side and minus the 30 over there. So force of friction is 50 minus 30, and so force of friction is 20. What unit? It's a force, so it has to be newtons. Okay, so 20 newtons is our force of friction pushing against that block. Okay, so 50 newtons is being pushed, 20 is working back against it. So overall, your net force is going to be 30 newtons. Okay. All right. So it's saying what is the force of friction? We got that already. And now it wants to know what mu is, okay, or the coefficient of friction of whatever surface this is. We know force of friction is mu times the normal force, and we know that that's 20. Okay, so let's try to find out what this mu is. Mu Fn is the same as the force of gravity because the surface is flat. Okay, so we know that force of gravity is mass times 9.81. So we know that it's going to be mass times 9.81 equals 20, because force normal is the same as force of gravity, which is mass times 9.81. So now we can go mu and then 5 9.81 equals 20, and solve for mu. So if we divide by 9.81 and divide by 5, then we'll have our answer. So 20 divided by 9.81 divided by 5. 0.408. Do I put any units on that? No, not for coefficient of friction. And it's between 0 and 1, so we're okay. And we know that this is going to be a bit more frictiony than a desk or something like that. And that's Newton's first and second law.